Thank you all for joining this training session on high performance computing. I'm Natalie. I'm a communications officer at Flanders Make, and I'm going to give you a short introduction to this course. It's a training part of the RebootSkills project, which is a European funded project, part of Digital Europe. The goal of this project is to help develop a skilled pool of talented digital experts in Europe by offering free courses on AI, robotics, IoT, and cybersecurity. The target audience for these courses is mainly employees from SMEs with some background in engineering, but who are interested in upskilling. And we also cater to unemployed people who are looking to get a competitive edge in their job search. The difficulty level of the courses is typically from awareness discovery up to intermediate level. We are Flanders Make, a strategic research center in Flanders. Our research serves one overall purpose, which is to support product and process innovation within industry. And that's why we conduct industrially driven, pre competitive technological research. We are not the only organization that is currently developing RebootSkills courses. We are in a big consortium throughout Europe with partners such as the University of Oulu in Finland and the University of Limerick in Ireland and other partners in Italy and Sweden. For this course, HPC to Edge, we focus on how AI models can be tailored to run efficiently on small embedded devices. I have the pleasure of introducing your teachers, Kurt de Grave and Marcel Aag. Kurt is a senior researcher here at Flanders Make. He is a specialist in the field of AI. He studied computer science and engineering science at KU Leuven, and his professional highlights include co-inventing several important machine learning algorithms. One algorithm is, for example, is used in the prediction of odor from chemical structures. At Flanders Make, Kurt designs AI algorithms for industrial innovations, such as the optimization of metal sheet forming, additive manufacturing processes, and product quality inspection. Kurt has used HPC clusters in his research since 2007. You don't see a photograph of Kurt, but rather an illustration that depicts some of his early work on predicting the efficacy of potential medicines. Our co-instructor is Marcel Aag, a PhD student at the Jülich Supercomputing Center and the University of Iceland. He obtained his Master in Science in Economathematics from the University of Köln, Germany in 2021. His research interests include large-scale machine learning on HPC systems with a focus on distributed hyperparameter optimization and neural architecture search. Marcel will contribute to the last section of this course. So I thank you again for joining this call, and I'll give the word to Kurt for the first part. Thank you.
Thank you, Natalie, for the kind introduction. Maybe we should also say something about the guidelines for this webinar, right? So you cannot record the session, but it is being recorded. And we will have Q&A sessions after each section. Okay, so this is an experimental manufacturing facility, and we use AI models to detect and correct defects in the produced parts. In such a manufacturing context, consulting an AI model in the cloud is just too slow, because by the time the answer arrives back from the cloud, the machine can have started its next layer, and the opportunity to correct any problem is spoiled. So therefore, you need the AI model to run locally. And in this particular case, it could be a server or a workstation near the production facility. But in general, you want to be able to run on a robust and low power and embedded device. if possible, something industrial spec. And that happens in many more cases, whether you want to serve users that are using their smartphone, or so there are many more cases for reduced latency and lower cost, and the enhanced reliability you get from nearby execution of an AI model. In other words, independence from cloud. So this session is in 3 parts. A longer part will discuss edge AI, or AI on embedded systems. And the next 2 sections are a bit shorter. They cover a very brief introduction on high-performance computing, and we will explain how we do hyperparameter optimization, so tuning AI models on using high-performance computing. In between, we'll have a 5-minute coffee break, and then we resume about at 11:05 approximately. In the first section is also, there are 3 parts. We'll discuss inference requirements, so the basic principles for AI inference. And then we'll discuss an experimental setup that we've built, and we'll share some of the measurements we've made of different devices on that setup. So yeah, most headline-grabbing AI these days is a deep neural network in one form or another. And there are multiple layers of neurons in it here. The minimal number is used, but usually it's many more. And each node here is a neuron, so computes its values from its inputs. And these inputs are weighted. So each line in this graph is, there is a number associated with it. And to execute this model, you need to store all of the weights, you need to retrieve them from memory, and you need to be able to do all of the computations for all of the neurons. Inside each neuron, there's not just a weighted sum, which is the computationally most demanding part of computing the neural network, but there's also a transfer function. And although this transfer function only needs to be computed once per neuron, it's important that the embedded device where you want to execute a neural network on supports the activation function that the designer of your AI model has chosen. Or if you are designing an AI model yourself, it's important to select from the available activation functions that your device, your target device, will support. The very cheapest and classic by now activation function is the ReLU, the rectified linear unit. So that's the hard corner curve here. But there are many variants that have different advantages. And so it's, yeah, again, important that your device supports it. Then in terms of computational constraints that we see, so there are 2 main classes of networks that are very much in use today. The simplest or the oldest one is the convolutional neural network. So here, this picture shows a single convolutional layer, a single convolutional filter. A layer consists of multiples, many such filters, actually. So on the left is the input, and on the right is the output, and in between is the convolutional kernel. So that's a small matrix. It can often be a 3 by 3 matrix, like here. And for each value in the output, this matrix is multiplied element-wise with the elements in the input. But the matrix is reused for all of the outputs. So this means that there are rather few parameters in our convolutional layer, only 9 in this case. But the number of computations we do with these few values is very high, depending on the resolution of the input. So this has implications for which device we can use to execute this type of network. The other case, the other very popular case is the transformer design or architecture. And so here, well, of course, this course is much too short to explain it in full, but so there are performance critical steps in such a transformer. And the main performance critical step, if your input sequence is not too long, is in the computation of these values, so the value key and query matrices, and these use each of their parameters only once. So that means that you need for each value that needs to be fetched from memory, you only need to do one addition and one multiplication. So the actual computation is much cheaper than the fetch from memory. So again, this has implications on which type of device you want to execute this network on. This is, let's look at a real example network like this. This is PVNet, a convolutional neural network. It takes a camera picture, like the example on the left, and it estimates the position of a specific object in the scene. And such a real network, there are several different type of layers. So it's not just one convolutional filter, it's many filters in a layer, and there are also the different types as you see in the legend. And many of those layers here have skip connections. That's also extremely common, and nearly practically all networks used today have skip connections. So that means that a layer retrieves its input from multiple previous layers. And so it just then sums its different inputs. So again, to run this network on any hardware, the hardware must be able to execute all of the operations and all of the activation functions, and also have enough memory to store all the weights for all of these layers. And also to store the intermediate results, because otherwise you cannot reuse the intermediate results later. So to summarize this, to be able to run a neural network, you need to ask yourself, does my device have enough memory to store the network and its intermediate results that are really required during execution? Can it compute all of the activation functions, and can it deal with the numeric type in my network? We didn't cover that, we'll cover it very soon. To know whether it can do the inference of the network, so the evaluation of the model, sufficiently fast, the computation throughput is most important, but memory bandwidth can also be the limiting factor. And the available the achievable effective utilization of the compute can sometimes be far below 100% due to various constraints and how well the network design fits the device. So yeah, there are many types of hardware when the simplest one is a regular CPU, as everyone knows, and almost everyone will also have heard about GPUs. So originally, GPUs were vector processors which could multiply vectors of numbers. But these days, a GPU also contains matrix cores or tensor cores, depending on which vendor you buy it from. They will have a different name, but so these are essentially matrix multiplication engines. A TPU is more or less the same as a matrix GPU, but it's especially Google who uses this name for its matrix engines. And then maybe also relevant, so FPGA is sometimes used for low latency evaluations of small networks. A device will come with memory, so there are different types of memory, and they differ in the available bandwidth. So how many parameters can you fetch from the memory per second? And on-chip SRAM is the quickest. High bandwidth memory, of course, the name is self-explanatory. There's GDDR, so that's the type of memory that is used for consumer level GPUs. That is a bit faster than regular computer memory, regular DDR5 DRAM. And then the very slowest type of memory is just to store it on a solid state drive, flash. In some cases, when you don't need to evaluate your network very quick, but you have a very limited embedded device, that can also be useful to still be able to execute something when, again, there is no time pressure. So the primary technique to scale down a network to either make it fit on a device or to make it run fast enough on a device is quantization. And so this graph shows why quantization is relevant. So this data is relatively old. It's hard to find very accurate newer data, but the truth or the base of this still holds. So what we see is if you train your network as normal on a FP32 number, so a full floating point or single precision floating point numbers, which is the standard for training, more or less, except for transformers. Then multiplying two 32-bit numbers takes a lot more energy, 20 times more energy than multiplying 8-bit integers. And also memory transfer is, of course, if you need to transfer 8 bits versus you have to transfer 32 bits, that's 4 times less work. And you also need a memory that is 4 times smaller. It's especially the bandwidth these days that is very important, and memory size, because multiplication gets better when your chip process improves. And memory costs remain much more similar. So we want to be able to compare the speed of devices. Now this is very tricky because it's very hard to grasp in a single number. Still, people try. And so the most common attempt to estimate the speed of a device is to express its TOPS, it's called, so tera operations per second, but this is an ill-defined number. But quite often it's the theoretical peak speed of how many multiplications or additions of 8-bit integers that a device can make. So it's the ability to compute, or if your device can do 1 TOPS, that means it can compute in 1 second the dot product of 2 vectors of each 500 elements. And usually each element is an 8-bit integer. But again, some vendors will specify their TOPS in 4 bits or in 16-bit floats, and so it's quite tricky, and there are a lot of misleading claims out there. So good to know is that 1 multiply accumulate is 2 ops. That's a universal truth. So if you are multiplying large factors of numbers, you multiply 2 elements and you add it to the total sum. That's 2 operations. So quantization comes in two ways. Either you can do quantization aware training, so where during training you try to estimate the noise and the skew that your later quantization will introduce, and you include that in the training of the model directly. So this gives the best quality quantized models. And the alternative is, if you don't do the training yourself, you use a pre-made model, is to do post-training quantization. And in most cases, you do use calibration data for that to minimize the reduction in accuracy of the model, because all quantization comes at a cost, and the cost is that the model will have worse predictions. So therefore, if you need to decide on quantization, then you should first ask yourself, do I actually need this? Because if your device is fast enough and capable enough to execute the full FP32 model, then by all means do that. So if your device supports 16-bit floating point numbers, then quantizing to just that will least damage the accuracy of the model. And in fact, yeah, most 16-bit floating point execution has barely any reduction of accuracy. However, yeah, many very low power devices, or yeah, if power is really a constraint, or you do need the maximum speed, then you need to quantize to 8-bit or maybe even lower. But then you do need calibration data, unless for some transformer large language models, there are methods that work without calibration data that also work fine. But for normal, smaller models, you will need some calibration data. Pruning is another way to reduce the size of a network, and also that comes in two varieties. Either you can reduce the number of filters or the number of layers in a network, so very coarse-grained pruning. However, this will certainly reduce the quality of the predictions of your model. And there is often the option to do finer-grained tuning, so where you sever individual connections between neurons, And you can often do that to some degree at a fairly low cost in quality of prediction. And some GPUs, many modern, many recent GPUs support this kind of pruning in the sense that they support structured sparse matrices. That is, that they can compute a compressed version of a structured sparse matrix as fast as it can process a dense matrix. And usually it's a factor 2, so you can then effectively compute with those kind of matrices at a 2 times speed benefit versus a dense matrix. With a often fairly low loss of accuracy, but your training needs to be specifically adapted to achieve this kind of compression. And this is also highly constrained, so hardware can only achieve this benefit when your the pruned numbers are very well spread over your data. So it must really be local interspersed holes in your matrix rather than localized or rather than concentrated blobs of empty places. Okay, there's also neural architecture search, which is used to optimize the parameters of your architecture, but we'll discuss this later when we come to the HPC part, because this is a very computationally expensive way, though also very effective. A final method to make good small neural networks is knowledge distillation. That is, you have a student network that learns from a teacher network. So we have training data on the left, and it is labeled, it has a gold truth labels. And when you pose it as input to the teacher network, you get a prediction at the end. When you present a training example to the student, you get another prediction in the end. And so you first train the teacher network fully. You use the gold truth labels to do the normal training, so backpropagation of the loss through the teacher network. And when that is finished, you train the student network using the output, the predictions of the teacher network. And magically, this happens to create better students than if the student were to learn from the source material itself. That's a bit paradoxical, but it's almost always true. And so this can create a student model often that very closely approximates the quality of the large and expensive teacher network. So teaching is very important in neural networks. When we look at embedded devices, or devices in general in this case, where we can execute AI models on, so it's important to be aware that there is a very large scale here. So the very smallest devices are microcontrollers. But yeah, you probably want to use very specialized AI models for them, not generic developed models, but there's a class of AI that's called tiny ML that makes models that are suitable for the smallest devices. Then even on fairly small Raspberry Pi-sized devices. Already manufacturers are including often small specialized inference engines that get around 1 TOPS or so. A smartphone is typically a high-end smartphone, especially, has much more compute capacity than that. So a high-end iPhone already has 35 TOPS. A good new laptop will get a bit over 50 TOPS. And the biggest machine in Europe that's even not yet finished, so the Jupyter supercomputer, for comparison, gets almost 50 million TOPS of inference speed. A device we will be looking at later that is the Jetson Orin AGX, and that's almost 300 TOPS. So that's a device that is also shown in the occasionally in the, well, actually in this slide. Okay, so we'll now talk a bit about an experimental setup that we built to solve the following concerns. So to do edge AI deployment, we need to overcome the fact that embedded device is resource constrained. That's what we talked about until now. But there's also, there are more general concerns. That is, how if you have a diverse range of edge devices you want to support, how are you gonna deploy your AI on these multiple devices with different properties? And also, how can you access your devices? How can you make sure they are working well and how they are performing? So to solve those challenges, for the first part, we looked mostly into quantization, so post-training quantization. In our setup, we start from a fairly small model, so no neural architecture search or other types of pruning were needed there. And yeah, so quantized models are smaller and smaller models are faster. And so you can achieve higher frames per second. So our test setup is a computer vision setup. So that's why our speed measure is frames per second. And when selecting a device, so you will have higher power devices that have also a higher compute speed and bandwidth, and lower power devices. So there is a trade-off to be made. You need to determine which speed you need, and then you can choose your device. So in our test, we included a good variety of different types of devices. So from GPUs to digital signal processors to FPGAs. And so all of these devices come with different tool chains and different constraints in the type of networks they support. So our goal was to benchmark all devices with the same AI model and to measure the KPIs, such as the latency of the inference and the power used. And we wanted to be able to repeatably or to reproducibly run this kind of experiment. So our setup contains 6 devices. There are 3 NVIDIA models here on the top, all NVIDIA Jetson versions. Those, of course, are equipped with the GPU. Then the KV260 contains an FPGA from the AMD Zinc UltraScale Plus series. The TDA4VM is a Texas Instruments board that contains a digital signal processor. And the bottom device here is also contains an FPGA from AMD. In our setup, we use Onyx-based model processing. So the quantization pipeline takes an Onyx model as input, and yeah, Onyx is one of the widely supported standards for storing neural networks ready for inference. We use a GStreamer framework to stream data in and out of each device. And we use a MLflow framework for monitoring and logging of what the network is doing on the device. So this is how the setup looks like. So it's sort of a shortened server rack. And yeah, it has its host PC to drive the thing, and power sensing, and of course the edge devices themselves, and they're connected to a camera, so we can run computer vision models, and it has a normal monitor for configuring it. So we start with a pre-trained Onyx model, in particular Tiny YOLO v2, which is a fairly old and very small model, but some of the devices we were using were very picky about the models they could support. So Texas Instrument SDK for the DSP is compatible with this Onyx model. And for NVIDIA, we had to modify the Onyx model to exclude non-maximum suppression, which is then executed on the CPU instead. So all of the devices we tested are hybrid devices, so each come with CPU cores on board, not only AI accelerators. All of the CPUs were ARM CPUs, ARM cores, by the way. And on the FPGA, the Onyx is modified to exclude also the detection stage. So only the backbone network is executed on the FPGA. So then this accelerated part of the network is then quantized, and the rest of the network is deployed on the CPU. We also added an option to combine 2 devices, so to reach maximum throughput and to optimize the number of frames that could be reached. This is how our setup works. So the MLflow server is the central part here. So each edge device only talks to via MLflow, and storage is mixed over MinIO, an object store that is Amazon S3 compatible, so an object store bucket. and a PostgreSQL relational database. So I have a UI where you can select which experiments you want to do, and it can show in real time the performance of the device, and then you can produce a radar plot of different performance characteristics. So to summarize, we have built this device agnostic setup for benchmarking edge devices. And so it's able to run experiments and log all of the important performance measures of these devices to benchmark them. Okay, so I'll show some results, if PowerPoint allows this. It had to think for a while. Okay, so this chart shows all of the devices. So the horizontal axis is the speed of inference in frames per second. The vertical axis is the power consumed by the devices measured by our setup. And so we see at the bottom corner here that an Orin Nano has very low power use. And so you see it returns 3 times. So that's because on the left is the CPU only inference. Then when you use the GPU, of course, the number of frames per second you can do is much higher. So that would be normal operation, because there is little reason why you would only use a CPU unless you're somehow very short on development time or so. And then when you quantize the number of frames per second you can do, is still higher, of course, but it will impact, as said, the accuracy of the model. That is not shown here. We see that the more exotic digital signal processor and FPGA reach comparable frames per second, but they are a bit more power hungry. And also the previous generation Xavier, Jetson Xavier model is approximately the same speed as a Orin Nano, but it uses more power. An Orin AGX of the same generation, but a bigger model with more CUDA cores, so a bigger GPU, is considerably faster. It can reach quite a nice speed of 182 frames per second if you do quantization. And then our combined model that uses both FPGA and GPU can reach 220 frames per second in our setup. Of course, at the cost of some additional power due to using 2 devices. So when we reduce this to a single dimensional performance number by just summing the area under the radar plot that weighs each of the performance metrics equally, which is what you may want or may not want. So depending on the weighting of the different features, of course, you will get a different result. But so given this equal weighting, for a low power use case, the Orin Nano was the best device. And for high throughput case, it's about ex aequo. So it really depends how much you want that extra speed. Okay, so there's now the option of questions. So we reached the end of our first part. After the questions section, we'll have a 5-minute coffee break, and then we'll continue with HPC and HPO.
It's now possible to unmute yourself and turn on the camera if you want to ask a question. So maybe please raise your hand so we don't all talk at the same time. We have one question in the chat. Yeah, sorry. So.
Yeah. Okay, so the question is, did we try the same with transformers? The answer is no. So as already mentioned, so some of these devices are quite picky in the operations that they support and the types of models that their tool chains can compile. So it would be quite a challenge to actually run transformers on some of these devices. It's much easier with GPUs, especially since NVIDIA is more or less a de facto standard. That's always the easiest to develop for. But no, we didn't try it with transformers. Yeah, so yeah, of course, you can, if the device is smart enough to run general purpose code, so you can code in it in C, then you can do basically anything. But yeah, a digital signal processor or an FPGA, you can not just write generic C for. Another question says, will we get a recording and the slides? And I'm not sure what the policy is there. Nathalie, will those be distributed?
Yes, we definitely plan on sharing the recording, and it's usually to discretion of the teacher if the slides are shared as a PDF file as well. Only to the
with some reservation, but okay, so there will be some resource package shared. Okay, so we'll have a coffee break of 5 minutes. So we start at 10:57. Okay, so it's 10:57 as announced, so we can continue. So the second part will introduce high performance computing, or HPC, which is colloquially known as supercomputing. This is Genius, one of the HPC clusters or HPC systems that we've been using a lot at Flanders Make in the last few years. We've been using several clusters. This one is located in Leuven at the University of Leuven. And such a cluster is really just an assembly of fast servers with a interconnect that allows a lot of the nodes to talk to each other to work together on one program, on one job. There's a list of the 500 fastest supercomputers on Earth. It's the top 500, so it's 25 years old, or that's to say the list has been published each year twice for all that time. And so in the latest edition of this list, there is one European computer in the top 5, which is the Lumi system in Finland. And so this is a system where European users have special access to, especially if you're in Belgium or you're in Finland, then those countries have contributed to this computer, so you get preferred access to it as a user. Now, the top 500 list, unlike in its early years, the last few years is no longer complete. So this list is based on voluntary submissions. And so the big tech or the big cloud providers these days they build huge clusters to train large language models, and they typically, they basically never submit them to the top 500, so we don't know about them, except little that is published in blogs or so. But for example, we know that just Meta alone very likely, certainly has at least one computer that would be in the top 5, so that would push Lumi out of the top 5. And they probably have several such systems. And that's just one big tech company. What are supercomputers used for? Well, the supercomputers that are in the top 500 are mostly used for mixed research with some industry systems and some pure academic systems. When you look at how are these systems built, so what do they contain? It's mostly just fast server CPUs. More or less generic CPUs is used in any server. And so the defining characteristic is more that they are interconnected with a local and fast interconnect. That can be either InfiniBand of a fast version of the normal Ethernet protocol. Due to historic reasons, top 500 calls it gigabit Ethernet, but it's much more often multi-gigabit Ethernet, of course. There's one thing that all supercomputer owners agree on. If your buying a system for millions or hundreds of millions of euros, you're not going to waste it by running anything else than Linux on it. And what we've been seeing the last several years is that these HPC systems are adopting AI accelerators. And when you look at the top 5, in fact, most of these systems, most of the performance of the systems is due to their accelerator sections. For example, the fastest computer in the list of June this year gets most of its performance from AMD Instinct MI250X devices, which are so someone is asking whether I'm sharing the latest slide. I'm not sure which slide is meant, but okay, but so you can look this up quite easily at the top 500 yourself. The list is due for refresh, by the way, in a few days, because there will be a November 2024 edition that's upcoming. And this is the June edition. And also the Lumi system uses such MI250X accelerators. So how does this differ from cloud? In a typical cloud environment, you have a hypervisor that is executing above the operating system. So this has a bit overhead, whereas on an HPC system, almost always you can run your programs on bare metal, so on a bare Linux kernel, which is faster. For the interconnect on a typical cloud system, there you get a good network connection, but it's best effort, and you're not sure where your job is going to be placed. If you want several nodes to collaborate with each other, the intersection interconnect is not always guaranteed. Whereas on HPC, you know what the design of the interconnect is usually, and it's optimized for low latency and sufficient bandwidth for good collaboration of all nodes. Also, the storage is sort of the same. So in an HPC system, you know the storage will be very near your compute nodes, whereas in a typical cloud, yeah, it can be routed from anywhere. And also important is that most HPC operators will employ professional sysadmins that are really specialized in optimizing computer programs to run fast, whereas in cloud you have to do it yourself, and often this is not a specialty of people. Then you do make mistakes, and it can cost enormous factor of performance. I continue saying typical cloud because, yeah, in the very large cloud providers, you can also rent HPC-like systems, but this will be extremely costly usually. And then for provisioning, so asking a new VM in a cloud is typically goes quickly, whereas in HPC, there is always batch job processing, which means there is a waiting queue, possibly. So you enter a job into a waiting queue, and then when the queue reaches your job, then it starts processing it. So the systems you can use, I saw many of the participants here are in Belgium. So I adapted this slide to Belgian situation. So for smaller computations, all universities have their own HPC system. That's a tier 2 system. And you would use that for jobs up to about 100 GPU days. If you need to run bigger computations, then you upgrade to the tier 1 system. There is one in Flanders. It's called Hortense, the current computer, because it's replaced every few years, as any computer is. So the current one is in the University of Ghent. And so this is suitable for approximately 100 to 1,000 or 1,600 GPU days. If you need still more computation, then you can use the tier 0 system. That's a European level system. And the currently biggest one is in Finland, the Lumi system I mentioned earlier. And yeah, that would be suitable for jobs that need more than 1,000 GPU days. If you are in a company, in a business, then you can also use these systems. Usually you will have to pay for it to use it, but it's fairly affordable. So the conditions for the university machines are university specific, but are similar to the other numbers. So in the Hortense system, it's charged at about €1 per GPU hour for a 100 GPU, which is a fairly good, very good GPU. One generation older than the best current one. Not counting Blackwell, which has a bit of a production issue. Then on Lumi, it's more or less comparable. So there is a project fee of €1,000, and then it's also €1 per MI250X hour. When you compare that to cloud pricing, then it's quite favorable, because renting an E100 in Azure, it costs €4.4 per hour. So to access an HPC system, the classical method is just over SSH, secure shell. And so it's a command line thing. You you open an SSH shell of your user number on a certain system, and you log in, and then you get a welcome screen that looks like this, for example, that shows the status of the machine usually, and then you can just type commands and run whatever Linux program you want. On some HPC systems, there is also the option of browser-based access, where you do not need a SSH client anymore at all. So the Leuven system, for example, supports this, and you can just then open a Jupyter Lab or one of the other environments in your browser, and it will run on the supercomputer. Once you're logged in, then such a system typically has a wide range of software pre-installed and pre-optimized for fast execution. Typically, the module system is used, so there are a few basic commands. You can ask for the available software, and you can search for it, and module load this or that software will configure your environment so that you can directly start the software. So to get a supercomputer to do your job, You use Slurm, which is by now more or less universal. So almost all supercomputers use this scheduling system to schedule their job waiting queue. So you write a small script like this, which specifies a maximum time that you want the job to run. If the job completes earlier, then it will just stop earlier. But you on a HPC system, you always have to specify a maximum to be able to allow the system to schedule other jobs. You specify the number of nodes, so the number of servers that your program will use simultaneously, and how much resources on each of the nodes you want to use. You specify which modules to load. You can run more and load more environmental stuff, and then you can run your application, here called app, and it will then be launched on all of the nodes that you asked for. So that still looks quite complicated, but fear not. So there's a recently developed tool to help you come up with this kind of scripts. In fact, it produces such scripts all by itself, fully pre-optimized. It can select from its repository and adapt pre-made scripts for you for specific systems. Though mostly the biggest supercomputers are supported, you can, if necessary, pick from another computer to at least have some inspiration, and you can select from multiple frameworks like PyTorch, Data Distributed Parallel, or DeepSpeed. And it will just output this kind of job script in full detail, ready to use. Okay, any questions about this part? So you can post questions in the chat. There is no coffee break. Well, not anymore. If there are no questions, we just continue with the most interesting part, the hyperparameter optimization part. Yeah, okay, so as a warm-up, so recall that deep learning network depends on weights that define the strength of connections between neurons. And so the process of training is adjusting those weights to better fit the training data. Training data for which you know what the right outputs are. And so the weights that are also called the parameters. Now, training only changes the weights, and it does not change the design, the architecture of the network, the number of neurons there are, the number of layers there are, which activation functions are configured for them, and so on. That's not part of training. It's just optimizing weights. But so there are a number of those design choices that are still very important for the performance and the quality of the predictions of your model. So also the method of training is very relevant to it. It's a determining factor in the eventual quality of the model you get. The learning rate, the amount, the number of examples that are in a batch when it is presented for training, the inertia of learning in that how you adjust the weights, and so on. So all of these hyperparameters, they're called, are important, but they're harder to adjust. And why is that? That is, weights are floating point numbers, so they're in a smooth space, and you can do gradient descent with back propagation, so you can follow the surface of weights and end up in a low point by just following gradient direction. Now the hyperparameters, those are either discrete or in any cases not differentiable. So that makes it much harder to find good combinations of them. So a combination of the hyperparameters, it's called the configuration of the network. So we will need to be prepared to expend a lot of computation to optimize them, because also to figure out how good a certain configuration is, we will need to evaluate the network. And to evaluate the network, we need first to train it. And training is already quite expensive. So doing this in a loop multiplies the total expense. So people have worked on different algorithms to reduce the number of trainings that are needed to find good configurations. And this is an overview of the types of algorithms that are used to achieve this. So the simplest are the algorithms that are model-free, so they don't try to keep track of a model of which configuration has which performance. There are more complicated algorithms which build a machine learning model, a meta model, in a sense, about how well your AI model will perform given a certain configuration. And then there are hybrid algorithms that combine the first and the second type. So among the model-free algorithms, the simplest ones are just random search. So just picking a totally random, random at uniform, usually configuration, and training it and seeing how well it does, and then picking another one and so on. You can do a grid search, that is an exhaustive search in configuration space. There's successive halving, and then refinements of it, hyperband and asynchronous successive halving. Or you can do evolutionary search. So this, a variant of genetic algorithms. And so among model-based algorithms, so Bayesian optimization is especially popular. So that builds a Gaussian process model that maps a given configuration onto how well the model will or is expected to perform, along with also an uncertainty estimate. And this uncertainty estimate will allow better decisions to which areas of the configuration space are yet unexplored and still likely to contain good configurations. So typically Bayesian optimization models are quite efficient in the number of evaluations that they need. A disadvantage, however, is that they're usually meant for quite sequential use. So the calendar time you need maybe more than if you evaluate a lot of models in parallel on your supercomputer. So successive halving algorithm, what does it do? So it starts with the evaluation of all of your configurations, or well, the number of configurations you want to evaluate or can afford to evaluate. But it does not fully train them, so it stops after only part of the training is completed. And at that point, that's the dashed line here, the first dashed line, it evaluates all of your configurations, all of your semi-trained models, and it retains only the best half of it, or some fraction of it. It doesn't necessarily need to be a factor 2 reduction, but can be any fraction that is retained, but the principle remains the same. So let's say only half of the models are retained. And then you do some further training to look how those models perform. And of course, most of the models will perform better after more training. And after a certain period of time, you look at all of the remaining models again, and again you throw away half of them, and so on, until you retain only one model that you fully train. So this way, you are not certain that you would end up with the very best model if compared to training all of the models and then evaluating them. But usually you end up with a quite good model, while saving a whole lot of compute effort to do the training for a huge number of configurations. So our preferred tool for hyperparameter optimization is Retool, though we have also used other systems like Optuna. And that is because, well, first it's open source, and it works very well in distributed environments such as supercomputers. And there are many of the state-of-the-art search algorithms built in that you can just select and run, including asynchronous sequential halving algorithm, hyperband, the refined version of sequential halving, and Bayesian optimization is as well supported. Plus, most likely the deep learning framework that you're using will be supported. The big two are supported, TensorFlow and PyTorch, but also several others that are slightly more exotic. And then it also can integrate with many other hypertuning tools, including Optuna. So we did an edge optimization experiment where we optimized a computer vision model, again, though a more powerful one than in the previous experiment that I described in the first section. So computer vision model for an NVIDIA Jetson RNA-GX, as you have already seen. And we interface between the HPC system and the edge device in a database, and with the purpose of building a model that has both fast inference and also high accuracy. So the accuracy is evaluated on the HPC system, but the inference is measured on the edge device, because it's quite hard to predict with high certainty how fast a model will, how fast inference will be. without testing it directly on your edge model. So during the rate tune operation, we configure or we post all new models into the database. Then the edge device will check the database and evaluate how fast inference is, return the results, and then the optimizer can use both target numbers, so the accuracy and the inference speed, to select better and better models. So now so Marcel Aag, also present here, has been a pre-recorded explanation of how this system works.
I will now show you how to launch RateTune from an HPC system. The HPC
Okay, so this shows the result of a bigger run of this experiment. So as you see, configuring the hyperparameters of a neural network is quite important because there is a quite large spread in both inference time and validation loss, so prediction accuracy. And so by evaluating many different configurations, you can find configurations that are high quality in both dimensions. So if you're interested in training on related topics, then well, there are more RebootSkills courses available. The Vlaams Supercomputer Centrum offers training regularly on supercomputer topics, and also EuroCC has many of those courses, and Flanders Make offers industry-oriented short trainings also regularly. We kindly ask you to fill in our feedback form. It's quite important for our funding organization that participants all fill in such a form. So please visit this QR code or as Nathalie posted just in the chat, you can click this URL. So you can do that now, and meanwhile we can also answer questions if there are any. So please see the chat for either the URL or to submit a question, or best both.
Yes, and once again, if you would prefer to say your question, you can unmute yourself if you like.
Yeah, we'll allow some time for filling in the feedback form. So I hope you all have found the URL by now. So we've seen a bit of an overview of AI at the edge and on embedded devices. We've seen a fast introduction to high-performance computing, and we have shown how hyperparameter optimization can be done on such a high-performance computing system to find good AI models. So thank you all for your attendance, and I hope to see you again in future trainings.
Yes, thank you, Kurt. And he will also be giving another training as part of the RebootSkills program, and that will take place in February. So stay tuned for that. If you are subscribed to the Flanders Make newsletter, you will definitely receive the invitation. Also follow us on LinkedIn to keep posted on that. All right, I don't see any more questions, so I think we'll close the meeting. Thanks again for attending.